I'm a medical oncologist, and so I've gotten involved in the field of medicine through the lens of cancer. But cancer is but a way station in human illness, and I think it's in many ways gives insights about all human conditions. So I'm going to talk a little bit today about starting with cancer biology and then moving into biology as a whole. I'm going to see if I can get this to work. Can you see that all right?
Yes.
From the discovery of the double helix in 1953 to the completion of the Human Genome Project in 2003, scientists have insisted that cancer is a genetic disease. I'm sure you've heard this. And so what cancer doctors have told us is that broken genes cause broken cells, and broken cells cause cancer. And we've all heard this, we've all read this, and we've all seen this. Now, based on that, we've had 72 years since the discovery of the double helix to figure out the genetic basis of cancer and fix it. I didn't see the LA Times today, but did anyone see that? Of course not. We haven't moved any closer to the cure of cancer since we discovered the structure of DNA. So we need to rethink some of the principles that have led us to the point where we are. Now, when we do that, we begin to realize that many of the things we've been told, the dogma that we have been told, may not be true. And so some of you may find that as I go forward, I'm going to be distressing or disrupting your thinking, which I think is very good, because we need to rethink many of the problems. However, I'm going to give you all a chance to leave before you take the red pill. Because from now on, you're going to think about cancer and perhaps all biology differently. This may be a moment of change for you. So I encourage you, if you don't want to hear this, to take the blue pill and maybe consider departing, because you may never be the same person. So let's take a deep dive into what we've been fed for 72 years. Cancer genetics, as we know it today. Now this is going to be very technical. I don't expect you to remember all this, and there's no quiz. There are 1,000 cancer genes. 1,000 cancer genes. 250 of them are known as oncogenes. Those are gas pedals. So they drive the tumor to grow and eat and divide and invade. Oncogenes. The other 700, more or less, are known as tumor suppressors. They're like the emergency brake on your car. So about a third of cancers are driven to malignancy, and another 2/3 roll into it, almost by accident. In fact, the most common cause of cancer is the loss of the cancer brake. Now to get a little deeper, to date, we have sequenced 1 million patients' tumors. This is where your tax dollars go. So we have taken 1 million people with cancer and delved deeply into what constitutes their genetics. So let's see what we found. Well, there are greater than 2 million coding and 6 million non-coding point mutations, 61,000 gene rearrangements, 700,000 abnormal copy number segments, 60 million abnormal expression variants. But cancer is a multi-gene process. Very, very, very few cancers are one gene. In fact, very few are 2 genes. Most of them are 3 or more. So for any of you who are mathematicians, you'll realize that for a cancer to succeed, it not only has to win the lottery once, but 3 times. That is, 1 in 1,000 times 1 in 1,000 times 1 in 1,000. As I wrote in the Wall Street Journal, every cancer patient is indeed 1 in 1 billion. If anyone in this office or anyone in this room was a cancer doctor, I would guarantee them that the patient they're treating is not like anyone they've ever treated before, nor like anyone they'll ever treat again. So let's reverse engineer cancer. There's still time to leave for those who don't want to be disrupted. Let's take this process backwards to the source documents and figure out where we went wrong. How did we goof this up so badly? Well, I'll tell you how. A normal cell in your body, a breast mammary epithelium, gastrointestinal tract cell, prostate cancer cell, gastric acid cell, finds itself in a state of deprivation. It doesn't have enough oxygen or blood supply, nutrients, hormones, growth factors, something. Cells deprived of something, just like someone pushed underwater and unable to breathe, or dehydrated, die. Cancer cells are programmed to die when they're deprived. So the cancer cell has a decision to make. Am I going to live or am I going to die? Now, if the cancer cell decides to die, we're done. It's over. No more problem. But if the cancer cell wants to stay alive, it has to adapt. It needs to learn to use something it didn't know it had. And that adaptation allows the cell to pull out of its toolbox genes, cancer genes, KRAS, BRAF, P53. There's 1,000 of them. So the cancer cell reaches deep in its pocket and finds something that gives it the secret sauce. The cancer cell is now able to stay alive despite the body's desire that it die. Every errant cell is dangerous. And the body, all 30 trillion cells in our bodies, is unhappy that that cancer cell has learned this trick. But those genes, the KRASs and the PIK3CAs, are a secret sauce that grants the cell longevity. So now the cell can stay alive. But what it uses to get there might be one of many different pathways. What I mean by that is I drive a 55 Buick, but during that same period of time, a 55 Chevy looks very similar. In fact, many cars are very similar because they're made up of tires and axles and steering wheels and chassis. So in fact, the cancer assembles different genes, but at the end of the product of it is really a drivable car. Now it turns out that the genes often can stand in for one another. KRAS can stand in for NRAS. NRAS can stand in for HRAS. BRAF can stand in for all of them, as can CRAF. So these genes, the cells, are using different genes to create a new phenotype, a new cellular biology. Not DNA, but cellular function, driven by this mixture of genes that the cell has selected. At that point, with convergence of the biological features, the cell looks around and says, well, wait a minute. Now that I can stay alive and I figured out how to do this, why in the world do I want to go back to work? I just as soon stay home and work from home. So this cell stops making milk if it's mammary, stops making seminal plasma if it's prostate, stops making acid if it's a gastric acid cell, stops making tears or mucus or whatever the job was, and just focuses its energy, time, and abilities on staying alive and growing. And that regression to the malignancy is the malignant state. So you have just learned that cancer genes are the toolbox of the cancer, not the driver. Well, if that's the case, then a lot of what we've been told, and a lot of what we've funded, may be incorrect. Cancer is not a gene that drives a cell, but instead a cell that drives a gene. Now that is a fundamental change in thinking, and it will be impossible to solve the cancer question genetically, period. What we need is a deeper understanding of cancer biology. One that comes from the three-dimensional reality of our lives. We are not information, we're not blueprints, we're not printouts. We are three-dimensional entities that thrive and exist in our environment. And so we need to go back to looking at cancer biology through biology through cellular functional studies to examine what this very complicated cell is doing. It turns out that the human cell is so much more complex than anything man can make. The most complicated thing man has ever made is an atomic nuclear submarine. That's the single pinnacle of modern engineering. A cancer cell is 1,000,000 times more complex. So when we want to learn from cancer cells, we have to have the humility to observe what's going on without necessarily driving, owning, or knowing what's going on. We have to remove the hubris of our current molecular biologists and examine cellular biology through the lens of biology, of what cells are doing. So here is an example of ovarian cancer cells. These cells have been removed from a patient's body, and we want to know what these cells are doing. Now, if we expose them to something that injures them, causes them to be unhappy, deprives them of something they want, they will die. So what we're looking for in the tissue culture environment are signals that tell us this drug, this condition, this growth factor withdrawal, this hormone withdrawal is damaging to the cell to the point of lethality. And interestingly, that lethality comes in many flavors. There's apoptosis, and necroptosis, and autophagy, and paroptosis, and ferroptosis. There's a whole bunch of them. Cancer cells choose how they're going to die when they're injured. And to be quite honest, I don't really care what route they choose, so long as they die. The only good cancer cell is a dead cancer cell. So here we have ovarian cancer cells that have been exposed to injury and died. And when they die, they're much, much more likely to die in the body, so we can now double the response and add 44% to survival simply by having the humility to be educated by the biology of this cancer. So here's an example of what we've already been able to do and published years ago. Patients here everybody started here with ovarian cancer, advanced cancer, and they were treated and treated and treated and treated. And then they came to me, and starting right here, going out months, these patients had a tissue culture study like I just showed you, and we picked the winners and losers. And right here, the people who had resistant tumors all died, and the patients who had sensitive tumors all survived. Or almost all survived. So when we can probe the biological features of these cancers and use their biology to select treatments, we win. What is it that causes a cell to die? Why does a cell give up? Is it because of its genetics and its DNA and its informatics and its blueprints? No. Cells live and die bioenergetically. They either make energy and stay alive, or they don't make energy and die. Now, many of you are not scientists, so you won't know that there are different organelles in the cell. But what I can educate you to is the information of the cell is in the nucleus. That's where the DNA lives. But the energy of the cell is in the mitochondria, the battery of the cell. And you're going to hear more and more and more about mitochondria because metabolism is here to stay. So the concept of cellular life and death is driven not by its information, but by its energy. And if we really want to cure cancer, we have to unhinge those genetic elements that lead to nutrient utilization and energy. So when a cancer cell is injured, it might die by apoptosis, or necrosis, or autophagy, or any number of ways. And the point is, I don't care. I just care that they die. So if we're going to look at energy, if we're going to look at cancer through the lens of energy, then we need to know what makes up the energy of a cell. And you will all know that there are hexoses, these are sugars, glucose. And there's also lipids, fats. And there's also proteins or amino acids. So if the premise that cancer is in fact bioenergetic and biochemical, if that's correct, and what I've just told you is true, we should be able to measure cancer by measuring metabolites, by measuring these chemicals. So what we're doing in the laboratory is we're taking a look at the blood of patients with cancer to see if we can find those metabolic signatures, those changes in metabolites. One of the metabolites that is fundamental to cancer is called glutamine. That's an amino acid. Glutamine is the most abundant amino acid, and it is a good substitute for glucose. And strangely, interestingly, breast cancer loves glutamine. I don't know why exactly, but I know it does. So I want to show you some data we generated in Paula Demora here in the audience, and some of my staff are here. It seems to disappear. At the front table. Those results come right from his work. So here, from the blood of 1,225 individuals, we measured glutamine. It's simple, it's an amino acid, easy. And glutamine content in the blood determined whether people had cancer. So here, high glutamine, healthy. Low glutamine, breast cancer. We repeated it with 169 individuals versus 154. High glutamine, healthy. Low glutamine, cancer. So now, we're beginning to see not the gene, not the DNA, not the mutation, but the product of the gene. The end result of genetic aberrancies. We focused on genes when it was the products of the genes and the functions of the genes. That's really where the action is. We need to get deeper. So can we do this in breast cancer? Well, we've already done that and published 1,225 individuals, highly touted article in the OncoTarget. But we can do this in every disease. Here's an example of ovarian cancer. Now this is a survival curve, and I apologize for the technical nature of the talk. But if you start off with these patients all walking in the door as they did in our clinical protocol, and having their blood drawn, and then going on to have surgery and chemotherapy, one group of these people did extremely well, and one group of these people did not do so well. And they all had the same p53 gene, and they all got the same chemo, and they all had the same surgery, and they were all of comparable ages, and the tumors looked the same under the microscope. But this group here, going out 5 years, we're doing extremely well, while this group, not so. The only difference, their metabolic signatures, how they make and use energy, what nutrients their tumors rely on. So we can do this in breast, we can do this in ovary, but how about the really hard nuts to crack? How about the cancers that kill absolutely everyone? Almost. Pancreas. If you have metastatic pancreas cancer, you have a 1% chance of survival. It doesn't really get worse. So we need to start re-examining what constitutes these lethal cancers. Pancreatic cancer is curable, but we're not treating it correctly. My greatest interest today, and what my colleague Paulo and I have just returned from Brazil for collaboration, and I will be having a discussion in 2 weeks with the University of Michigan, is to get to the basis of pancreatic cancer and fix it. That's my goal. So here is a survival curve going out 13 years. Every patient here had metastatic disease, and some of them survived very long. And the survival correlated with their metabolism. Every one of these people had a KRAS mutation. Almost every one of these people had a p53 mutation. Most of these people had a CDKN2A or B mutation. Many of them had a SMAD4 mutation, but some of them died very quickly, and some of them lived 14 years, and that correlates with how they ate and used energy. Cancer, possibly all diseases of the human, maybe less about this and more about this. We are the products of our metabolism. and what we eat, and what micronutrients and what macronutrients we consume and use determine our biology. So if we use cancer as a way station in illness, and we now examine other diseases, can we turn this microscope away from cancer cells and look at all cells? And I think we can. Here are the leading causes of death in the United States today. As you can see, the vast majority are heart disease and cancer. And then there's a lot of other accidental deaths and things that occur. Cardiovascular disease, to cancer, to Alzheimer's, to Parkinson's, are metabolic disorders. I know you've been told that the ApoE4 gene is going to cause Alzheimer's or whatever. I don't believe it. Because people with ApoE4 don't get it, and people without ApoE4 do get it. So the gene story is bunk. We need to get deeper into the biology of our physiology so that we can solve these problems. These conditions remain largely undetectable with current methodologies. We need a window on our phenotype, our biology, our three-dimensional functionality, to begin to understand disease and the treatment and detection of disease, and to anticipate and even address conditions. And my favorite quote from the literature is here. Next generation metabolomics, which is what we're studying, this is a metabolism studies in our test tube environment. Next generation metabolomics allows the pre-symptomatic identification of metabolic disorders before irreversible organ damage has occurred. So instead of treating advanced disease and stenting the cardiovascular system and giving chemotherapy and treating type 2 diabetes, wouldn't it be appealing to find the metabolic signatures that predispose to these conditions and address them? People with elevated branched-chain amino acids have a tendency toward diabetes. People with lipid aberrancies have a tendency toward dementia. You can find these. You can find them today. And we think that over time we can address them. So longevity, which is the buzzword on the front page of the Wall Street Journal every week, longevity is nothing more than good health over time. What we need in medicine now is not to treat advanced disease, but to identify and prevent disease predispositions. And if we do this, all of the money we spend on advanced disease can be saved and used for other purposes like buying books. So imagine a future where we're not confronting these established diseases. How appealing. Here's where we'd like to go. A roadmap of health that identifies early in the course of life the conditions and predispositions that might lead us to states of illness, so that we can begin to identify what foodstuff, what micronutrient, what vitamin, what supplement, what exercise program, what sleep pattern might prevent the illnesses that we have come to think of as inevitabilities. We need to move more toward a rectangular life curve where you live very well until something goes wrong and you die at 97 or 111 or whatever. I don't think anyone will live forever. Well, I understand that Putin and Xi Jinping want to get transplanted organs. I'm not in favor of that. But we need to begin to examine lifestyles, micronutrients and nutrients, simple things that may in fact address illness before they become illnesses. And I think that's just a brilliant opportunity at hand today. So we're launching that. We just launched in Brazil. We're now commercially viable in Brazil. So Metabolomics, our new startup, is going to offer these tests for patients. Some of the people in the room already have them. And these are tests that we'll be commercializing in November. And they're not that expensive. And they give you signatures of health. They give you an idea of where you're veering off the road so that you might pull the steering wheel back away from the curb and get a longer, better life. Health span. Not lifespan, health span. So with that, I'll finish, and in deference to our colleagues in Brazil, I say thank you. Muito obrigado.
Thank you, Dana Buchanan. I wonder if there's anybody in the longevity gurus that are out there like Brian Johnson or anybody like that these days that you think are onto using what you just told us in their work?
Well, there's an enormous interest. Thank you for the question. Also, you're an early convert to good, healthy food, so I appreciate the question. There are zealots in this field right now who are doing very nutty things and jumping into freezing water baths and all kinds of continual red light exposures. And to be honest, there may be merit to some of those. The problem that I have, I mean, I've given lectures like this before, and one of the things we talk about is there is no diet or lifestyle that is right for everyone. See, as unique and as different, I don't see anyone in here who is a double Geiger or a identical twin. And unless you're an identical twin, whatever is good for you is unlikely to be good for the person next to you. Yet, we have a collection of people who are dictating ketogenic diet and calorie restricted, low glycemic and high fat and Atkins, and all of them are good for the right person. So from our standpoint, we think that we should know what our predispositions are, what our deficiencies and excesses are, and address them uniquely. I think that people like that are, they're using generic interventions to try to extend longevity. Maybe it'll work, but the trouble for me is, for example, if you don't tolerate high protein intake, and many people don't, they have urea cycle abnormalities, we found them in the general population. If you take a very high protein diet, that's bad for you. If you have certain lipid deficiencies, and you take a ketogenic diet, and you're eating whole cream for breakfast, that's bad for you. So the point is, I think we need a set of metric of our health. I understand what these people are trying to do, and I hope it works. But I would rather measure and adjust accordingly.
You talked about good metabolism, bad metabolism. I'd like to just get a sense of how you define that. And I also want you to just comment on your point of view about estrogen or lack thereof vis-a-vis breast cancer recurrence.
Interesting questions. Good metabolism and bad metabolism. What we are finding, what we have discovered, what we have coined the term of, is inborn-like errors of metabolism. Now, there are conditions, they were originally described in 1909 by Archibald Garon. There are conditions that children are born with, so that when the children eat breast milk or get formula, they become ill. We now know that there are 2,000 inborn errors of metabolism, and what we find in our studies is that we develop inborn-like errors of metabolism. What I mean by that is, when you eat a lot of sugar, or when you become very dehydrated, or when you are protein deprived, your body adapts. And that phenotypic adaptation may be good for you or bad for you. But because you don't know what you're doing at the time, your body reprograms. This is actually true. The genomic term for this is genomic reprogramming. And the cell epigenetically changes its genetic makeup to respond to this new environment. So what you wind up with is the byproduct of lifestyle and dietary intakes that are themselves unhealthy. Now, question, what if you were to address that? What if you were to reverse that and correct the excess or deficiency? would you be able to reprogram back to health? And I have at least one very interesting example. One of our friends, one of our longtime friends, whose son was exactly the age of my son Adam, came to me and we ran some tests, and he had not been well for some time. He had left his job in San Francisco. He was ill. He was living at home in the basement. He wasn't really going out. He was depressed, and the family were looking for psychiatric assistance. And when we ran his blood quite by accident, he had a urea cycle abnormality. He had a amino acid metabolism deficiency, and all we did was change his diet. And he got better. I mean, measurably better, noticeable by everyone. So there's a real hope that we can conduct what we call interventional metabolomics, where you actually go in and fix this. Now, we've only done it in certain cases, but I've had some dramatic examples of it. Your second question is quite a large one about estrogen and breast cancer. Estrogen, as many of you may or may not know, is protective against breast cancer. Women who are perimenopausal who take estrogen supplementation have a lower incidence of breast cancer. If they have not had a hysterectomy for other reasons, they have a higher risk of endometrial cancer. So what you're doing is playing off breast cancer versus endometrial cancer. Now, breast cancer in and of itself is more lethal than endometrial cancer or uterine cancer. So you could play the odds, but the question is loaded because it's really very unique and individual to each person. I wouldn't want to be giving medical advice, but estrogen supplementation, at least low-dose estrogen supplementation, is actually probably underappreciated as an intervention. Yeah.
Thank you for the great presentation. On a little bit of a different note, there's been some announcements of some serious cuts in cancer research and other things at NIH and other places. Does that concern you? Do you think there'll be consequences to that? Do you think there'll be underfunding?
Well, I'm sorry, I'm not sure I understood the question fully.
There was an announcement I saw a few days ago that said that at the federal level they were cutting back on cancer research.
Yeah, I mean, I think research is brilliant. I mean, we publish papers all the time. What I think the problem is that we fund bad research. And what I mean by that is if you want to look at really productive research grants, they're mostly in Canada. I went to medical school in Canada. And the reason I say that is that the Canadian government doesn't have money to waste. So when the Canadians fund a research project, it almost uniformly provides actionable results. Americans fund crazy stuff. I mean this. And so as a result, we fund a lot of dumb research because we have too much money sloshing around. I would be all for funding research. I mean, we benefit from funding research. So I'm not saying we shouldn't fund research. I just think that we should not only fund one kind of research. See, if you want to get a grant, and I've been through this my whole career, if you want to get a grant today, you'd better say DNA in every sentence. If you say biochemistry or metabolism, no money. But the answers may lie there, and the problem is we have a self-perpetuating research program where someone has a good idea and they get funded. And then they go all the way up the ladder to senior faculty. And then the only people that get funded after that are the people that agree with them. And we're seeing this in publications. Harvard University had to retract 71 peer-reviewed papers last year because they were not founded in truth. They were making up the data. So when I say that we should be funding research, of course, we benefit from funding all the time. Paolo DeMora and I did that study I showed you of ovarian cancer, that was funded in part by NIH money. And we appreciate and support that. But I think we don't always fund the best studies. It's like they say, it's not what you know, but who you know.
We have another question over here.
Thank you so much. This was so interesting and informative, and as a fan of Nikola Tesla, I'm delighted to see that someone is looking at energy as opposed to DNA informatics. So thank you for doing that. My question is, I was offered a blood test that could detect, 300 types of cancer. Is that legit?
Yeah. Let me explain. It's not to say that cancer genes are not operational or active or doing things. They are. But the cancer genes are the toolbox of the cell. You see, it's not, this is what's called a paradigm shift, because you take something you already know and you explain it differently. So what I've tried to show you about the red pill and the blue pill was, cancer is not a gene that drives a cell, but a cell that drives a gene. And when you get that understanding, you realize we have to be more global in our assessment of what we're really measuring and doing. So we've been trying to go in and fix the blueprint. It would be like having someone build you a building, and then you decide that the garage isn't large enough, and you go back and change it on the blueprint. Sorry, building's built, contractor's been paid, you can't go back and fix the blueprint, and that's what we're trying to do. Now, you were talking about a gallery test. That uses the Illumina platform and screens for genetic elements, and it's touted wildly. Now, the gallery test is designed to identify cancer early, when the cancer genes are just showing up. Okay, well that's a very attractive idea, but if you look at the data, which I wish you wouldn't, it turns out that early stage cancers are not detected. Early stage cancers, do you know what the sensitivity of the gallery test for stage 1 cancer is in lung cancer? 29%. Well, thank you very much. That's a $900 guess. So as far as I'm concerned, if we were to look deeper into the biology of cancer, we would realize it's not a matter of the genes, but the cellular environment that calls those genes up. It's like recruiting the military. If you don't have a fight, you don't need the military. So what you want to do is dampen down the deprivations so that the cells don't look for ways out. All 30 trillion cells in our body want to stay alive, and if they did, there wouldn't be enough room on this earth for people, because cells must die. We achieve homeostasis where the number of cells in our body doesn't increase. We don't keep adding, we're not 50 feet tall. So the point is, this dynamic of life and death is critical to our existence. And the dynamic of life and death gets disrupted by cancer, and the disruption is a cell wanting to do something, and it uses the gene. It uses the gene. That doesn't mean to say that the gene isn't found. It's just not the driver. Yes?
Thank you very much for very informative lecture. I'm MD also, but I'm retired MD and I'm not an oncologist. But I have a question. I never heard about the metabolic effect on the cancer. People treat with the chemotherapy. So my question is, do you have certain kind of test for metabolic for different kind of cancer to give hope to the patient? And can it work? Or any treatment, metabolic treatment which will work with chemotherapy? You know, there are different kind of cancer, so I'm sure that different kind of genes are affecting, but you say genes are not important that much. It's the cells which make the genes. So is there any hope for these people? All these things, this is just the research, or you are just treating the patients?
It's a great question, because if cancer has a distinct metabolism, that is, if cancer only likes dill pickles, or only wants ketchup, or will only eat grass-fed beef, then all you need to do is to restrict access to dill pickles or ketchup or grass-fed beef, and you have nixed the cancer. And so in fact, despite my dismay over what we found in all the gene testing, slowly people like Craig Thompson out of Dana-Farber and doctors at MD Anderson and other groups around the world, we are a small coterie of people who begin to realize metabolism is the direction we have to go. And some of these people have developed small molecules that inhibit this. I give a lecture, and I will give it again in a couple of weeks in Tucson. I give a lecture and I lay out all the drugs that are used for cancer in the pancreatic environment. And then I look at all the drugs that we're now testing for pancreas cancer. And the drugs that we're testing now are metabolic inhibitors. Inhibitors of glutaminase, inhibitors of mitochondrial function, inhibitors of glycolysis. And so inhibitors of dehydrogenase or all of these different substances that are already out there that we're not using correctly. So I hope I answered your question. that I think this isn't just some gee whiz science. This is really maybe a better way to treat cancer, but B, a better way to find disease in general. And so what we want to do is extend this beyond cancer, which is already a late stage phenomenon, to predispositions to disease, so that you can massage the person's health back to well-being. And I hope I answered your question.
Thank you so